Hi, this is Roshan Naik, and in this video I'll be covering the features that are new to version 1.1 of Castor. These features could be broadly classified into two buckets. The first set of features are essentially an evolution of the features available in 1.0. The second bucket is the set of features which are basically new stuff. This is a broad outline of the features that are evolving from 1.0. And here's the features from the second bucket, which are features that are basically new. Here's some more of them. In the rest of this video, we will be basically covering some of these major features in some detail. Let us start with the features in the logic reference type. Here we see the logic reference li being initialized with I. The semantics here is to make a copy of I, and that copy will be referenced by li, and also the copy's lifetime will be managed by li. It is sometimes useful not to make copies and actually refer to the original object. For this, 1.1 introduces a new constructor which allows you to provide the address of the object you're interested in managing, and also specify with the Boolean argument whether you want the lifetime to be managed or not. Here, since I is on the stack, we do not wish to automatically manage the lifetime of I using the logic reference, so we specify false for the second argument. This ability to refer to pre-existing objects directly without making a copy of them, and also not own their lifetimes, is quite useful because it allows you to share objects between the logic paradigm and the imperative or object-oriented paradigms, and just allow a smoother blend. Changing the value of li can be done easily in 1.0 by simply assigning a new value to li. This again implies copy semantics. In 1.1 you have also the ability to change the value by having li refer to a different object but not make a copy of it using the setPointer method. In this case, we will be pointing to a new object that's allocated here, and we have decided to take ownership of this object's lifetime. Next is a small enhancement which allows us to check if two logic references are co-references. We use the bound method to check if li is actually bound to lj, and in this case, since li and lj are co-references, this assertion should succeed. Next is a change in semantics for the assignment operation between two logic references. Let's consider these two logic references li and lj, and assuming lj is initialized and li is not. In 1.0, assigning li to lj as follows would lead to an exception because li is not initialized. In 1.1, this behavior has been changed to reset lj instead of throwing an exception. This is a semantic change between 1.1 and 1.0. And that's primarily the changes coming to the logic reference type. Before concluding the topic on logic references, perhaps it's worthwhile mentioning important limitation of the current implementation. Logic references to const objects cannot bind with logic references to non-const objects. This would currently give you a compiler error. This is primarily due to some implementation complexities, which we hope to have it resolved in the future. Now let's turn our attention to the enhancements around iteration over containers. In 1.0, we have the item relation for this purpose. It has two overloads, one which works with an iterator pair, and the other one which works with a logic reference to an arbitrary container. In 1.1, we introduced two additional overloads. one which takes a logic reference to a set and another one which takes a logic reference to a STD multiset. Now these overloads have been introduced primarily for efficient lookups when you're dealing with sets or multisets. This overload here, when used in the lookup mode, would enumerate every single value in the container to see if the value exists in the container. Since this is not a very efficient way of dealing with sets or multisets, in particular when you're looking for a value, we have these two additional overloads which perform faster lookups. The multiset overload could succeed more than once if the value being looked up occurs in the multiset multiple times. One important thing to keep in mind is that these overloads require J to be a logic reference to a const object, primarily for preventing accidental modifications to the values in these containers through the iteration variable J. For working with the custom set-like containers or set-like containers from third-party libraries which allow faster lookups, we have the item underscore set relation, which takes a logic reference to such a container. Here set T is any container type that conforms to the standard associative container requirements, where the key type and value type is the same. So for instance, you could use item underscore set with the TR1 unordered set and unordered multiset, or other such containers from Boost, for instance. In generic code, it might be desirable to use a single item relation and not use two different relations like item and item underscore set to deal with set and multiset versus third-party or custom libraries. For such cases, you could define a custom overload for the item relation, in this particular case for a custom hashed set, that merely forwards the invocation to the item underscore set relation. For working with map-like containers, we have the item underscore map relation, which takes a key and a value argument in addition to the container. Here mapT is any standards conforming associative container where the key type and value type are not the same. So basically anything like STD map, multimap, and so are the upcoming unordered maps, for instance. The interesting thing about this relation is that you could do lookups either on keys or on values. So if you initialize the key to a certain value, you would get all the mapped objects associated with that key. Similarly, if you initialize value but not key, you will get all the keys that have the same object associated with it. And similarly, you could leave both key and value uninitialized or initialize both of them, depending on whether you're interested in enumeration or performing lookups. And finally, in this series, we have the R item relation, which allows iteration of the container in reverse. Here, CONT is any arbitrary container which supports reverse iteration. Now let us turn our attention to some convenience relations introduced in 1.1. Here we have the write all relation, which is useful for printing all values in a sequence to standard out. Here we're printing all values in an array and here we're printing all values in the vector to std out. You could also print to a file stream, for instance, by using the write all to relation and explicitly specifying the stream to which you are interested in printing. So for instance, if you may be interested in printing to a file stream. Let's examine the output that's generated by write all. I'm going to build and run this program now. Here we can see there's a delimiter between the values and there's also a sequence terminator. In this case, the value delimiter defaults to a comma followed by a space, and the sequence terminator is a new line. We could override these defaults by explicitly specifying them. For instance, you could have space separated values and a tab, for instance, as a sequence terminator. Or you could just specify only the value delimiter. Let us now take a look at a few other relations: pause, skip, zip, and eval. Pause is a very simple debugging facility. It's quite primitive. It simply waits for an enter key to be hit on the console before continuing execution. Now, here's some code for computing the intersection of two arrays. I have two arrays here, array 1 and 2, and I've loaded the second array into a set. This is the logic for computing the intersection. I'm enumerating the values in the first array and then looking them up in the set. I'm using a set here because lookups are faster on sets as opposed to raw arrays. And here's the code which puts the evaluation into motion and prints all the values in the intersection. So if you're interested in watching the values trickle out of the first relation, the first item relation, you could just say pause and print the value of I, which will stop every time this relation generates a value, print the value on screen and wait for a key press, and then continues execution. So let's just get rid of this print statement here so that you can actually watch the values. I'm going to compile and run this code. It has now printed 3, and each time I hit the enter key, it prints the next value. So you can watch the values trickling out of the first array and halt the execution at that point. You could also, for instance, watch or pause the execution on values which failed the intersection computation. For instance, you could say XOR pause I. So each time the lookup in the set fails, you could pause the evaluation and watch the value that failed the lookup on the set. Pause is no different from write. The only difference is that it actually waits for a key press on the console. You could also print string debug messages. And if you're interested in actually evaluating an expression, like an IL expression, you could just use pause underscore F relation and give it an IL. We'll see skip later. Now let's look at zip. Zip takes two relations as arguments and evaluates them both each time it is evaluated. Zip continues to do so until one of its arguments fails. So in this case, we are using the zip relation to iterate over both arrays simultaneously. Basically, this is parallel iteration over the two arrays. So we are printing the values iterated in parallel over here. Now let's take a look at the output. You can see the values from the first array in the first column and the values in the second array in the second column. Notice that there's only 5 values being printed because the first relation succeeded only 5 times because the first array has only 5 values. You could use zip for instance, computing the parallel sum of the two arrays. You could say sum is I plus j and sum is a logic reference, and here you could print I plus j equals sum, and now you can see the parallel sum being printed. You could also nest zip to perform parallel iteration on more than 2 relations. So for instance, you could do k is an item in the set So here we have nested zip as a second argument to the first zip. This will provide you with parallel iteration over 3 containers, and you can continue to do so on more relations. Now finally, let's take a look at the eval relation. Eval simply allows us to invoke a regular function from a declarative expression. In many cases, you might have some tasks that you could do on the side using an ordinary function call, which you would like to have invoked through a declarative expression. Let's take a simple example to illustrate this idea. So here we have a string stream which contains a sequence of numbers. We are reading those numbers out from the stream as integers because I here is an integer. And then we are filtering out the values that are extracted from the stream using this predicate. This basically will give you all the even numbers in the stream. And then we proceed to print those values. Let's say, for instance, you would like to collect all these values that are extracted from the stream before you filter out some of them. For this, you could use eval. And let's say you are interested in collecting all those values in some vector. So for this, you could use eval. And we'll actually require a little helper function called push, which takes an ordinary vector by reference and the value that needs to be pushed onto the vector. Now you could just invoke push and pass the vector v and I as arguments to push. So as we're reading the values from the stream, we are collecting them into the vector before we proceed to filter them out. Here, notice a little subtle detail. Well, I forgot to introduce the vector itself. So let's define a vector into which you're going to collect all these values. So here v is a logic reference to a vector, and push, being an ordinary function, does not have its parameter types as logic references. So there's an implicit conversion from logic reference type to ordinary types. So that's one way to do this, but in this particular case, you could simplify this by using the eval underscore mf routine, which allows us to invoke member functions directly. So you no longer need the push method, the push function here, and we have eval underscore mf, to which we pass the vector on whom the method needs to be invoked and the arguments to the method. So this would give you the similar effect, and now you could print all the values in the vector using the write all relation that we saw earlier. So this was a simple example where we used eval and eval underscore mf relations in order to perform some side jobs in the middle of some declarative expressions. Preferably such side jobs should not introduce side effects which alter the behavior of the rest of the declarative expression, nor should they introduce any side effects that require to be undone as part of the backtracking process. The other thing worth mentioning is that eval also accepts ILs as arguments in addition to ordinary functions. So this concludes our section on these 4 relations. Now let us take a look at the enhancements to the IL facility. The 2 major enhancements are, one is the introduction of new named ILs. We shall take a look at some of these in a moment. And the second enhancement is improved support for string literals in IL expressions. Let's take a look at the code in a moment to see what these named ILs are. Before describing each of the named ILs that are introduced in 1.1, let me quickly recap the named IL facility so we understand the motivation behind it and its usefulness. Here's a simple example where we compute the parallel sum of two vectors. We have Vi and Vj, the two vectors of interest, and we're using the zip relation to iterate over the first vector and the second vector in parallel. So I is the values from the first vector and j is from the second vector. Then we proceed to unify the sum of I and j with s using the unification function eq_f, which unifies the result of evaluating a function with the logic reference. We could further continue to consume the value of s, but in this case let's just limit it to computing the parallel sum. Computing the parallel sum is easy enough that we can express the core operation using just the basic overloadable operators, as in this case. In some cases, using just the basic overloadable operators may not be sufficient. For instance, if you're interested in computing the sum of the logs of these two values, in such cases we do not have a built-in log operator. And for solving this issue, we can create custom named isles, which are simply function objects that can be composed with other operators to create lambda functions. So log here is not provided by Castor. You could create it quite easily, and I'll take a look at how we can create these named isles in just a moment. But first let me cover the basic named isles that are already provided in Castor. Here's a list of the named isles introduced in 1.1. First is ID, which allows you to capture an object by reference. It's quite useful in situations where you cannot make copies of the objects such as C in, C out, or it is not desirable to make copies of the objects and you want to actually reference the original object. Then we have call and mcall, which allow you to invoke a function or a member function by name. Then we have get for accessing data members, at for invoking the index operator, and create for instantiating objects. This deprecates the older create with from 1.0. I'll take a look at a few examples with each of these in the next few slides. Here we have ID, and in this expression I'm using ID to capture C in by reference and then read a value from the stream and then write it back to C out. So in each of these cases, C in and C out cannot be copied, so therefore it's essential to use ID here. Next is call. Call is used for invoking functions or function objects. In this first example here, I am unifying the value 3 with the result of invoking std plus with the arguments 1 and 2. In the next two examples, I am unifying some variable x with the result of invoking some function foo. In the first case, it's with 2 arguments, and in the second case with 3 arguments. Now these last two examples are interesting because here we are assuming that foo has 2 overloads, one with 2 arguments and the other with 3 arguments. But we do not need to explicitly disambiguate the precise overload that needs to be invoked in either of these cases because the designer is intelligent enough to deduce the fact that in the first case we need to pick the overload with 2 arguments and in the second case the overload with 3 arguments. This particular lack of need for explicitly disambiguating between overloads is generally true across Castor wherever you are able to pass a function or a member function as argument to be invoked. For more details on this particular feature, refer to the description of the eval relation in the reference manual. Next is mcall and get. Mcall is used for invoking member functions and get is for accessing data members. Here I'm using mcall to obtain the length of the string. Mcall's first argument is the object on which the member function is to be invoked, followed by the address of the member function and followed by any arguments. In this particular example, I'm using mcall to check if the length of the string is equal to 5 by passing this IL expression to predicate relation. And here's get. The first argument to get is the object on which the data member is to be accessed, followed by the address of the data member. In this case, I'm simply printing the data member first of the pair to cout. In both cases, mcall and get, one thing to keep in mind is that the first argument cannot be just an ordinary variable. It should be a logic reference to an object. And finally, we have the two named ILs at and create. At is merely a facility for invoking the index operator, since the index operator cannot be directly used in IL expressions. Here in this example, I'm printing the first character in the string to cout using the at named IL. Create is for instantiating objects on the stack. In this example, I'm performing parallel iteration again on the two vectors vi and vj, and from each of those values, the pair I and j, I'm instantiating an std pair using the create IL and unifying it with b. The template argument to create specifies the type of the object to be instantiated, and the actual arguments are simply passed to the constructor of the type. That completes our coverage on the named ILs that are provided in 1.1. Now let's take a brief look at how to define your own named ILs. Although this ability to define your own named ILs is not new to 1.1, I'll just take this opportunity to introduce this topic briefly. Here, we're performing a parallel iteration over the two vectors again. Vi and vj are the two vectors, and I and j are the iteration variables. And then we're unifying s with the sum of the logs of I and j. Now let's define the named IL LG. This is a simple two-step process. First, you define the function, which we are invoking here. This function returns the actual function object, which will do the real work of computing the log. The one little trick here, or the magic, is that the return type LG_IL, which is the function object, is being wrapped in a template type called ILE, that's an IL. This is what actually allows this ordinary function object to be used in IL expressions where it is composed with other operators or named ILs. The second step is to define the function object which does the real computation. It has two simple requirements. One, it has to declare its result type explicitly as a member type def, and obviously the second requirement is that it needs to define a function call operator which has no arguments. Here's where all the computation will occur. In this case, let's just for simplicity use the standard log computation algorithm. And that's the basic steps involved in creating custom named ILs. First is to write the function which returns the function object that is actually wrapped in the IL template type, and then actually defining the function object which does the real work.